morning, everybody. I am really excited about today and this CyberSight webinar that is focused on artificial intelligence in ophthalmology. I'm Malik Kahook. I am professor of ophthalmology at the University of Colorado. I am an artificial intelligence novice, so I'm coming into this as a student, super excited about the panel that we have and about the potential to learn from everybody. Before we get started with the introductions, I just wanted to cover some stuff that you can take with you after the session. Most of you have been to orbis.org as well as cybersight.org. If you haven't, I think it's time for you to go and see all of the information that you can learn from. You see the screenshot that I have on the right-hand side with access to the library as well as multiple classes that teach you everything from ROP to glaucoma, some of the basics of medications, lasers that we use in ophthalmology, just a wealth of free data. So please sign up. If you're a teacher with residents and fellows, please have them sign up and participate as much as possible. I also want to thank at the top here, Lawrence and Jonathan, the magic behind CyberSight. Lawrence is the one who's running things behind the scenes here, and they're working very hard on all of these sessions. So I'd like to thank them for all the work that they're putting into it. And thank all of you. It's not easy to attend these sessions, especially at different times around the world. For me, it's early morning. For many of you, it's much later in the day and perhaps getting towards the end of your day. So thank you for that. We're always trying to improve these sessions. You can go through Orbis or CyberSight to give some feedback, and you can also contact me on Twitter. That's probably the most interactive way to say what you like, what you didn't like. You can see me and Gabriella sort of arguing over things on Twitter, which I'm going to start doing with her pretty soon now that I know her handle. But you can also participate, ask any questions as you go along with the journey of learning about artificial intelligence, and I'd love to learn from everybody. So let's talk a little bit about who we're going to hear from today. As I said, we have people from all over the world, different time zones. We also have speakers from all over the world, different time zones. And in no particular order, I'm going to read off some of the bios here that are extremely important, I think, to just kind of understand the depth of the field that we have speaking to us today. The first one is Pearse Keane. He is professor of artificial medical intelligence at UCL Institute of Ophthalmology and a consultant ophthalmologist at Moorfields. He is originally from Ireland and received his medical degree from the University College of Dublin, graduating in 2002. In 2016, he initiated formal collaboration between Moorfields and Google DeepMind. And I think that's when a lot of us got to know Pearse and a lot of the work that he was doing. It was covered heavily by media, and I think rightfully so, because it was really a shift in the way that we do things. He jointly led work to develop an early warning system for age-related macular degeneration, has done extensive work in other areas of ophthalmology, and is really leading the effort to change the way that we practice ophthalmology in clinics. So welcome, Pearse. Michael Abramoff is probably known to the majority of people who at least dabbled in artificial intelligence. He is fellowship-trained retina, computer scientist, and entrepreneur, which is putting it lightly. He's the Robert Watsky Professor of Ophthalmology and Visual Sciences at the University of Iowa, with a joint appointment in the College of Engineering. He is founder and executive chairman of Digital Diagnostics, formerly known as IDX. This is the autonomous AI diagnostics company that was the first in any field of medicine. Think about that, the first in any field of medicine to get FDA clearance for an autonomous AI. He's also a pure academician with authorship of 300 peer-reviewed publications. He's been cited over 41,000 times and has multiple issued patents. Chris Leung, who I was talking to before we started this live session, haven't seen him in a very long time, really excited to see him, have learned a lot from him through the years with his expertise in OCT. He's a clinician scientist with research focus in glaucoma detection and diagnostics, has his master's in molecular medicine from the Imperial College of London, and obtained his medical training and doctoral education from the Chinese University of Hong Kong. He completed his clinical and research fellowship with Bob Weinreb at UCSD at the Hamilton Glaucoma Center. And he is playing a key role in advancing a lot of the new concepts that will allow us to access early diagnosis of glaucoma and detection of other ophthalmic diseases. He's certainly a pioneer in using AI in glaucoma, and that's what he'll be lecturing on today. Gabriella Lanouette is a full stack machine learning engineer working for Orbis. So she's an insider coming to us with the first lecture today to talk about what Orbis is doing. She's a part of CyberSight. She develops algorithms for CyberSight AI tools, which can detect common eye diseases in mere seconds. Gabriella received her undergraduate degree in applied mathematical sciences from the University of Connecticut and holds a postgraduate degree in applied artificial intelligence and machine learning from Columbia University. So welcome, Gabriella. Dr. Ciku Mathenge, who I've been getting to know over the past year and a half, is a consultant ophthalmologist and director of training at the Rwanda International Institute of Ophthalmology and professor of ophthalmology at the University of Rwanda. RIIO offers community services, conducts research, and trains ophthalmic workers, including the first ophthalmology residency program in Rwanda. She has her master's in community ophthalmology from the University College of London and was the first certified researcher in Africa on the rapid assessment of avoidable blindness survey methodology, or RAB. In 2006, she was awarded the first Sir John Wilson Fellowship and thus pursued her PhD at the London School of Hygiene and Tropical Medicine. She has conducted extensive research in retina, and I'm going to try and drag her more towards glaucoma with some of the collaborations that we're going to do, and I'll see if she comes kicking and screaming towards glaucoma. But I'm really excited to have her and her expertise. She'll be talking about one of the research projects that she did that I was fortunate enough to participate with as well in a recent manuscript. So I'm looking forward to hearing that. And last but not least is my colleague here at the University of Colorado, Jayashree Kalpathy-Cramer. She was recently appointed as the chief of the new division in our department, Division of Artificial Medical Intelligence and Ophthalmology at CU School of Medicine. Her research interests include medical imaging, analysis, machine learning, artificial intelligence for applications in ophthalmology, radiology, and oncology, so she can bring her expertise from other branches of medicine. Previous to this, she was at Harvard and co-director of the QTIM lab and the Center of Machine Learning at the Martinos Center. She's an electrical engineer by training. She worked in the semiconductor industry for several years. She decided that she was being paid too well, so she decided to go into academia, and she's now focused on the applications of machine learning and modeling in healthcare. She's very passionate about the potential of machine learning techniques, and I could attest to that. She's been a great teacher, and I'm super excited to learn from her, not just on this session, but also now that she's faculty with us, to learn every day from her as we interact on research projects. And we're going to start with the first talk that will cover the first handful of minutes as an introduction to CyberSight AI. So Gabriella, I'm going to hand it off to you, and look forward to hearing your talk.
Thank you, Dr. Kahook, and thank you all for having me. This is really a humbling experience and pretty exciting. I'm excited to hear the rest of my panelists. So today I'm going to talk about the Orvis AI ecosystem. As Dr. Kahook mentioned, I'm a full stack machine learning engineer at Orvis. So this all really starts with CyberSight, and our goal is to build a global audience of healthcare professionals. So our digital services with global reach and a big emphasis on global. And to do this by upskilling local health workers through free access to telemedicine and learning capabilities. We want to lower the barrier of entry to your services. So as long as you have a device with internet connection, you should be able to get access to the same learning material that you would in the best medical training program. So the funnel models, this is for eye care specifically and applies to us, but does apply to many areas in healthcare. Capacity is very important, and we want to give everyone the opportunity to be checked. So this journey from screening to treatment has a big emphasis and capacity overload and not much expertise. So this is the most pressure on the system. Many skilled workers are required in many locations, and the systems can't cope. So fewer patients, this leads to fewer patients being assessed and treated, and AI can help with both of these issues. So this is a normal screening workflow. We start with patient imaging, which is then graded by a human grader on the ground, and then reported. And if everything is good, we circle back, and then this leads to referrals and treatments. But in low resource environments, there's a major shortage in grading, which then leads to delays and missed opportunities in reporting, which leads to missed referrals and missed treatments. And because there's 20 times fewer ophthalmologists per capita in low middle income countries, this is a big overload. So AI can increase the capacity with assistive AI. This does tackle the capacity issue and provides the confidence needed to participate in the clinical workflow. So this can be done with AI, with the automated interpretation of retinal images using deep learning. This includes referral recommendations, disease grading, anomaly detection, and lesion visualization. And this is actually a fundus image that you would get returned from CyberSight AI. As you can see, there's the vertical cup to disc ratio, biomarkers, hemorrhages, exudates. You would get a DR grading score for diabetic retinopathy, a glaucoma score, and many other disease markers. So CyberSight provides this additional context in a telemedicine human in the loop workflow. It's a standalone tool that's integrated in existing screening workflows, and it's free of charge in low middle income environments. So is AI useful when implemented on the ground? A recent study that we ran and was led by Ciku in Rwanda showed that patients were more likely to adhere with referral recommendations when receiving instant AI results. And Ciku will speak more on this in her talk. So thank you for listening to my talk. Upload AI-only cases today at cybersight.org. And if you're interested in using our AI tools or collaborating, get in touch at support@cybersight.org.
Yeah, that's great. I think one thing that I should have said at the top that you just mentioned is the fact that CyberSight does have this collaborative consult service that can be a peer-to-peer as well as using the AI system. So I encourage everybody to go visit that. We're going to move on to the second talk, and that's going to be Jayashree Kalpathy-Cramer. She's going to talk about the do's and the don'ts of data collection. So we're trying to avoid bad info in, bad info out. And Jayashree is going to talk to us a little bit about the ecosystem around starting early AI projects and how best to collect data and deal with data in AI. So Jayashree, you're up.
Thank you for the introduction. And as was mentioned, I was going to talk a little about the data. As I think most people here are aware, especially modern AI techniques really benefit from having lots of data and are really only as good as the input data that goes into the model building process. As a data scientist will tell you, the part of curating and annotating the data is the least, sort of one of the least enjoyable tasks and takes the most amount of time. Again, for most projects, the data curation can take up to 80% of the time frame. Well, the fun part of it, which is the model building, is very small in terms of the time and resources that go into building these data sets. So machine learning typically is described as a system that gets better at a task through experience. What that means is the more and more data that it sees. For instance, when you're building an AI model, the better the model gets. If the data are more diverse, the model again is more robust. The key ingredients to building machine learning systems is, again, data is the main thing. It's what goes into the system. It can be tabular data like a spreadsheet. It can be images. It can be a combination of images and demographics. So a variety of data inputs can go into your machine learning model. And hopefully at the end of it, what we get is something that transforms the input, whether it's images alone or images plus other things, into an output. And there's many other things in terms of considerations, in terms of what kind of algorithm, how do you measure error, and so on. Typically, we talk about supervised and unsupervised as two. There are many types, but these are two commonly described kinds of machine learning. And in supervised learning, which is what we typically tend to see published, we need lots of ground truth. So along with each data, you need some label. So for instance, if you're creating a glaucoma diagnosis model, you might need the images plus the output diagnosis. If you are looking for ROP or things like that, again, we have data and we have labels. In unsupervised learning, we essentially are looking for clusters in the data. We don't need the ground truth labels. And in some ways, these are things to think about as you're starting to build a model in terms of how do you curate a data set. There are many different kinds of models that people build. Deep learning is very common today, but support vector machines and random forests and trees and others are common previously and might come back into fashion again. Another thing to think about, again, during the data collection and curation process is what is the output of the model. So very often we see these are the kinds of models that we see most oftenly. So for instance, we have classification models, and this can be for any disease. So in this case, we do a lot of work in ROP. So for instance, we might be interested in understanding if this particular image from this baby represents plus disease or not. And very often these classification models tend to be binary. So is a disease present or absent? And again, when you're thinking about the data that you're collecting and the labels that you need, that's the kind of information that you need is, along with this image, do you have a diagnosis? Sometimes we might want to do segmentation, and in segmentation, the goal is to delineate the region of interest. So in the case here, we might want to delineate the vasculature, and so we have a segmentation model for the vessels. In other cases, we might want to delineate drusen or other characteristics from the image. Detection is similar to that, but very often in detection models, you use a bounding box to essentially highlight the area of concern. So this is, again, an example of a detection model with hemorrhages and different things sort of outlined. You can also have regression models, and this is often used when you're looking at severity of diseases. So if you have normal, mild, moderate, severe, or where you might use ordinal regression, or if you have a numeric value, you might use other kinds of regression models again. And so it really depends, the annotation effort and the curation really depends a lot on the tasks. So at what level are we doing the annotation? Is it done on the patient level? Meaning, do you just know for this entire set of data associated with that patient, if it's like a positive or negative? If you have multiple images from that patient, for instance, if you have like a fundus and OCT and something else, are you doing it on image level or just on the patient level? If you have three-dimensional data, are you doing it on a frame or a slice or something like that? Or are you doing on a pixel or box level? And depending on that, the effort that goes into the annotation and creating the data set can be quite different. In sort of very, if you want to do segmentation, it takes a long time. On the other hand, if you're building a model that's a segmentation model, the size of the data set that you require can be much smaller. So there's definitely trade-offs between the amount of effort that you're putting in to creating this data set, as well as the time, the number of images that you might need for it. Where are you getting this, the ground truth from? Are you getting it from the patient record? Is somebody prospectively annotating it? So that's another question to think about, is where are the annotations coming from? How are you doing it? Are you parsing the EHR to get the ground truth? Are you having somebody do it? How many cases do you need? One consideration is that the ground truth can be quite subjective. We see a lot of variability between raters. This is from ROP, and just asking a set of 8 experts on the same set of images, whether it's normal, pre, plus, or plus, you see quite a range of opinion for the same set of images. So as you're creating the data sets, again, something to think about is what the consensus is and how do you create ground truth. Again, you can get it from EHR. So this is a typical workflow. You get the data, you might have it from the EHR, or you might have somebody do a prospective evaluation. You typically pre-process your images, and that might include normalization, cropping, augmentation. You build your model. There's many different ways to do it. What architecture, what type of parameters? Are you using AutoML to do it for you automatically? And then how do you independent? The evaluation piece is also really important. What is the ground truth? What is a metric? What are you looking at it on an independent data set? So in the case of ROP, for instance, again, a 3-level system for plusness, we can see that in the case of our data curation, we had the spreadsheet that we got with this kind of information. We also wanted to then have multiple raters annotated, and eventually we get something like a plus and a normal or categories like that. We then do some kind of pre-processing and imaging. We might normalize the images or do some kind of making it such that images coming from different cameras look more similar. We might crop out everything but the image region of interest in ROP because we're looking at vascular aspects of the image. We might do a segmentation, we might flip, we might rotate, and so on. And then there's many frameworks that are open source and publicly available that you can use for your model building. Typically, classification models are evaluated using an ROC curve, and you can, again, look at the performance of your model as well as performance of individual raters. And this is something we see typically presented as well, again, highlighting the issues that we have with rater variability. So if you look at the literature, there's thousands and thousands of publications, or at least hundreds of thousands of publications in ophthalmology. And it's getting to the point that it's getting quite straightforward to build these models if you have the data. But some of the cautionary tales we've seen both from ophthalmology and other diseases, other areas in radiology, et cetera, is that these models can be brittle. They are not self-aware. They're not explainable. They can be unbiased or not fair. They don't generalize well. So if you build a model in one institution and give it to your colleagues across the pond or across the country, they may just not work well. There's a lot of data heterogeneity issues. So if you have different populations, we build a model in the US and take it to India, different camera systems with different fields of view, different protocols. Suddenly we're expecting to see posterior pole images, and we see this image on the left here. It really might mess up our model. Image quality is something that needs to be considered carefully as a precursor to the classification model. And different biologies and different populations might affect the performance. In COVID, for instance, they found that there was a lot of the models were not useful, and we saw hundreds and hundreds of models published, and one of the biggest problems is these Frankenstein data sets. So really the problem is the data going into building these models. The model building part is easy and it might seem like it's working, but if the data going in is not good, it really can cause lots of problems. One of the big issues is what we call shortcut learning. And the networks are somewhat sort of lazy, and they pick up the spurious signals that might be things like scars in images or markers, things that are not really what you're looking for, but are associated with the output that you're interested in. And this can really mess up your system. Different scanner types might look different, and you might have quite a bit of variability there in such a way that if you train on one scanner and test on another scanner, it may not work. So if you train and test on the same imaging device, it looks great. If you train your model on one device and test it on another device, it may not work at all. And so thinking about how do we sort of create these nice, beautifully centralized data sets is something that we should be thinking about. But there's many challenges with central databases because of privacy and so on. International regulations, again, this can be quite challenging to do that. So federated learning approaches can be useful there. AI can be biased, and so we need to think about that. And then to re-emphasize, we really need data from all over the world in order to build these models that are useful everywhere. So just to summarize the do's and don'ts, please think carefully about building diverse data sets, and diversity refers to demographics, disease presentation, institutions, devices. In terms of creating the annotations, to the extent that you can, multiple raters is important. We need to really check for bias and confounding in the data. It's very easy to accidentally leak data between sort of your training data and your test data set and give you an inflated sense of performance. So thinking carefully about how not to leak data is useful. And then the data really need to be representative. So yeah, to summarize, garbage in, garbage out at some level, and really the data are key to creating good, robust models.
Thank you so much, Jayashree. I think you've illustrated a lot of the history of sort of what has happened in the past, but also what the struggle might be to get to where we're aiming to be in the future. And that's what Pearse is going to talk about. So let's hand over the space for sharing to Pearse Keane, who is going to talk about concept to reality. How do we get from where we are today to getting to more closer to the clinic? And we can go over this in the Q&A session because I think a lot of us will have questions about this. But Pearse, take it away. Tell us how we're going to get there.
Thank you, Malik, for the nice introduction. And just let me say thank you for inviting me to this event. This is just wonderful. So I'm going to speak about going from concept to clinical care, or maybe the way that I would like to think of that is going from idea to algorithm and going from code to clinic. So I guess I've already been introduced at the start of this session, but just to repeat some of that, I'm a consultant ophthalmologist at More Assistive Ai Hospital in London, and at More Assistive I specialize in the treatment of retinal disease. And I'm also a professor of artificial medical intelligence at University College London. And although I'm not a computer scientist or an engineer, I've somehow come to find myself leading a multidisciplinary clinical research group that aims to develop and apply artificial intelligence in healthcare. And one of the things that we believe is that ophthalmology is one of the medical specialties at the forefront of this transformation, and we think can be an exemplar for other medical specialties. I'm fortunate to be funded by UK Research and Innovation, and these are my financial disclosures. So as Dr. Kahook mentioned at the start, back in July 2016, I initiated a research collaboration between Moorfields Eye Hospital, where I work, and the artificial intelligence company DeepMind. DeepMind are, one of the world's leading AI companies. They're founded in 2012 in London. And the nice thing from my perspective is that 2 of the 3 co-founders are from London, and 2 of the 3 co-founders are graduates of University College London, which is university affiliated with Moorfields. And in 2014, they were acquired by Google. And even the best thing from my perspective is that they're based in the King's Cross area of London. So that, for those of you who know London, that's just 2 stops away from Moorfields on the London Underground. Now, we started this collaboration back in 2016, and the idea was to work together to develop a deep learning system that could evaluate OCT scans of the macula and could be used by people without expertise to triage the scans to identify those patients with the most sight-threatening disease, to get them in front of a retina specialist as soon as possible. Now, the collaboration began, in 2016. We worked hard for a couple of years, and in August 2018, it was very exciting to publish the first results of the collaboration in Nature Medicine. And essentially, we described a deep learning system that was able to assess these macular OCT scans and evaluate them for more than 50 different retinal diseases, and had a performance on par with some world-leading experts at Moorfields for the kind of triage of those conditions. Now, it was also very exciting that this was featured in the cover of Nature Medicine, and of course, this being AI, there's a lot of hype around it, and so it was very exciting for us that we got global media attention. Now, of course, that was very exciting because I've done a lot of research before, which I've really put my heart and my soul into, that probably was not read by very many people. So it was nice to get a lot more attention on the research. At the same time, though, it's also a little bit awkward because there is a huge amount of hype around AI. And the fact of the matter is, although we think this has great potential, we haven't actually saved the sight of millions of people yet. Now, let me just show you the algorithm in action. So this is running on a macular OCT scan from a patient in their 40s at Moorfields with very poorly controlled diabetes. And essentially the network consists, or the AI system consists of 2 neural networks. The first neural network does segmentation, which Jayashree talked about nicely in her previous lecture, but essentially it means it delineates between 10 and 15 different anatomic parameters on the OCT scan. In fact, you can see in the bottom right there, you can see all the different anatomic parameters. So in this case, you don't have to be a retina specialist to see that this patient has diabetic macular edema. It's delineating all the intraretinal fluid cysts on the scan. Now, the segmentation network then feeds into a second neural network, which is a classification network. And you can see the outputs of this in the top left. So in this case, classification network is recommending a semi-urgent referral to see a retina specialist, and it's giving a diagnosis probability across different classes. So it's saying macular retinal edema in this case. So, for example, this could be used in the context of some sort of community diabetic retinopathy screening program to help identify people with macular edema to refer, prioritize getting them seen urgently by a retina specialist. So, I'm here to talk about going from code to clinic. And so the question then is, that was 2018, now it's 2022. Where do things stand with this system? And are you in fact saving the sight of millions of people with this? And so I thought I'd tell you a little story about a friend of mine and someone called Ken Kukier. And Ken is a senior editor for The Economist magazine. And basically, Ken contacted me in March of 2021 in a little bit of a panic because he had suddenly lost vision in his left eye. I think we were in a lockdown, a COVID lockdown at that time in the UK. And so, he wanted some advice about how he could get that sorted. Now, I was able to direct him to go into Moorfields and get seen in the emergency department at Moorfields and get sorted out. But one of the things was that when he was in there, because he had written about our work in artificial intelligence before, he was really curious to see it in action as he was going through the system. So he's asking the receptionists, where's the AI system? And asking the nurses, when am I going to have the AI running on me? And everybody was looking at him like, what is this guy talking about? And so, because in fact, the AI system that we've developed isn't yet being used in the real world. And so a few days later, he sent this tweet where he kind of gently teased us a little bit, where he said, AI is a fraud. I went to Moorfields for emergency eye surgery, and instead of DeepMind's cool algorithms diagnosing me and robot surgeons, I had to accept the excellent, skilled, thoughtful care of human medical staff. What a disappointment. Now, as it happens, the condition that he had is not something that would be diagnosed with an OCT, and therefore the AI system that we've developed for OCT wouldn't really be of any benefit for him. But nevertheless, he makes a good point that the system, that he had written about is not actually in the real world. And so he very graciously invited me on his podcast to talk a little bit more about these real world challenges. Now, I'll touch on that briefly now. So one of the key challenges is around the technical maturity of these algorithms. And one of the things that I've, has really struck me in the last few years as a clinician is that the piece of code that is used to typically accompany a research paper in a journal, that's like a piece of experimental code. That's nowhere near really a piece of software that could be deployed at scale for human benefit. The other fact is that these systems, while they're very exciting, there's plenty of ways in which they can go wrong. And so they really require robust clinical validation. And it's one thing to show good results, as we had done on an in silico retrospective data set, a very different thing to do a prospective clinical validation. And that's a very, very important component. And then alongside that, you need to have regulatory approval in most countries for these algorithms to be used. And of course, that's something that requires considerable expertise and effort and resources. But in some ways, those are kind of well-defined challenges. Some of the really gnarly challenges are around actually, how can these AI models be integrated and delivered within current healthcare systems? What are the business models? What are the economic models around the use of these systems? Will they make business and commercial sense? And then, will healthcare professionals and doctors, etc., actually implement and adopt these systems? And in fact, we're still very, very early in AI-enabled healthcare in beginning to answer these questions, not just in ophthalmology, but across other specialties also. And so actually, I was reading recently a biography of Thomas Edison, and it occurred to me that there's a lot that we could learn from his story, and in fact, a lot that we can learn about the light bulb. And so, this was an article that I was reading related to that, about when Edison lit up Manhattan. And essentially it says, on September 4th, 1882, the electrical age began. And that was the day that Thomas Edison's company flipped the switch on his power station on Pearl Street in New York, providing electricity to homes at a price comparable to gas. And it was fascinating to me to read about this story, because actually the light bulb had been invented by 20 or 30 different people over the previous 25 years. But the true beginning of the electricity age was when Thomas Edison could bring things together, and he could bring together reliable sources of electricity, a distribution system for that electricity, a connection system to light bulbs within the home, and then some sort of meter to be able to quantify the usage that was required. And that was the true beginning of the electricity age. And so what I think is that for us to go from code to clinic, we really need to have a network of innovations. It's not just an AI model, but the systems that it can be embedded within. So we're really trying to think about that in the way that we implement our own systems. At Moorfields, we're building a new hospital. We're already trying to think about what are the new pathways of care into which we can deploy AI systems in the future, and how can we have the flexibility for new and as of yet unimagined deployments. But really, for me, the really exciting potential of AI is, can we use it to bring specialized expertise out of hospitals into the community and potentially into the homes of patients in a future? I think we have a real opportunity in that regard in ophthalmology. Certainly in the United Kingdom, there's a lot of potential, because in community optometry settings, we now have OCT being used as a standard part of almost all eye tests. You have the big chains like Specsavers and Vision Express and Costco, as well as in independent optometry chains deploying these systems. We're beginning to put in place the telemedicine infrastructure to link those community services with the hospital. And so I think that will allow us to bring together this network of innovations. So just to conclude then, this has just been a very much a whistle-stop tour about the potential of some of the work that we're doing in AI in healthcare. I do believe it has the potential to transform ophthalmology. We're still in the early stages yet. And if anyone would like to get in touch with me, as promised, that's my email address. Thank you very much.
Thank you so much. And I'll be emailing you after the session with questions as well, along with, I'm sure, a lot of other people. So thank you for getting into some of the basics of the reality of where we are today versus what not just the community at large is expecting, but also physicians, your colleagues are expecting. Hey, when are we using AI? Are you using AI in your clinic? I think I asked you that when you were visiting here a few months ago. So we'll get into that a little bit and talk about the reality of diseases like glaucoma and retina. And we'll start it off with a discussion around glaucoma from Chris Leung, who will specifically address the applications in glaucoma. So Chris, take it away.
In today's talk, I would like to cover the opportunity, challenges, and unmet needs regarding the application of AI in glaucoma. The diagnostic performance of AI for detection of glaucoma has been investigated using fundus photographs, OCT scans, and visual field. And in this systemic view and meta-analysis published last year, including 503 AI studies in medical imaging across different specialties in medicines, 82 of them pertain to ophthalmology, among which 22 are in the space of glaucoma, and 17 studies had fundus photographs as the input, and 5 studies had OCT as input. The conclusion is very encouraging because we see very high diagnostic performance, reaching an average area under the receiver operating characteristic curve of 0.93 for fundus photograph studies and 0.96 for OCT studies. These studies show huge opportunities of AI in glaucoma care. One potential application is to aid non-specialists to detect glaucoma. And AI is also useful to help quantify optic nerve structures when conventional algorithms fail to work. Here is a scan, an OCT scan, a wide field scan we obtained from the Plex Elite Swab Source CT, and we're looking at the retinal nerve GCIPL thickness distribution. We see loss of the retinal nerve of the GCIPL of the superior temporal side, but you also appreciate these not very good loss of artifacts, loss of the emotional loss of segmentation errors, which is actually quite common in wide field scan. But here we're applying a deep learning segmentation. We're able to quantify this optic nerve head structure, this retinal nerve fiber layer, GCIPL layer much better with deep learning algorithm. So not only AI is able to help identify, detect glaucoma, but it can also to help help the time when the conventional software algorithm fail to quantify the structures. Telemedicine plays a major role in healthcare delivery in the era of COVID. With increasing opportunities for home monitoring of health data, AI can help actually revolutionize how we should feel that OCT can be monitored. Glaucoma screening is another potential application of AI. It's an important topic, but I don't think I have time to cover that in detail. So what are the challenges in applying AI in glaucoma care? Although AI algorithms have a high diagnostic accuracy in glaucoma detection, level 1 evidence, clinical trials supporting the applications in glaucoma care is lacking. One major limitation, one challenge we face is when we interpret the OCT AI or fundus photograph AI studies, one challenge we often see is the inconsistent definition of glaucoma. Back in 2016, the World Glaucoma Association consensus meeting, a group of glaucoma specialists talked about how to diagnose glaucoma, and they defined glaucoma as a disease which is predicated on the detection of a thin retinal nerve family and narrow neoretinal rim. But in this consensus meeting, we didn't discuss how thin is a thin retinal nerve family and how narrow is narrow neoretinal rim. So that makes actually the diagnosis or the defining features of glaucoma difficult to set in many studies. And here we see slides summarizing 3 AI studies using fundus photographs as input. And what we see here is that they use different features, they use different criteria to define glaucoma. And some of them actually quantify glaucoma as having a vertical cup-to-disc ratio more than 0.9. And you can see some of those mention about using rim width, and some of those mention about using our NFL defects as defining criteria. Likewise, for OCT studies, AI OCT studies, the defining criteria is also not consistent. Here is 3 studies, again, using different types of definition of glaucoma in defining the ground truth. Some of them use visual field, some of them use cupping optic disc features, and it's really hard to get a set of well-defined criteria across these studies. And another challenge here is we see greater variability. A lot of studies actually rely on fundus photograph to determine the presence of glaucoma, but we know inter-observer agreement in determining glaucoma damage was only moderate even among glaucoma experts. So this huge inter-observer agreement or huge inter-observer variability actually led to the question that whether this labeling of data set, some of these studies use thousands or tens of thousands of fundus photograph images, whether these images were graded reliably, consistently is always a big question mark. And even if we are able to come to a consensus that, for example, in this picture, we see the cup-to-disc ratio is pretty big. Many of us would agree the cup-to-disc ratio reach the definition of some of these studies. We have 2 studies using fundus photograph AI studies. In these studies, they define glaucoma as any one of these features, including vertical cup-to-disc ratio bigger than 0.9 in one study, and then the other study is bigger than 0.95. Now, even though here we have an optic disc fitting the exact criteria mentioned in the paper. But when we look at the retinal nerve fiber layer, we see the retinal nerve fiber is actually pretty normal for this eye. So this is probably related to physiological cupping, and this is no evidence of optic nerve damage. There are other technical limitations that may hinder the reliability of detecting optic nerve damage. We all know about the challenge in screening out poor quality images, motion artifacts, before we actually train the AI algorithms. Not only having these challenges pose perhaps some biases in our training of data, But even if we have good quality images, here we have 3 eyes. We see these OCT pictures of the retinal nerve fiber layer. They have good signal strength. We don't see any motion artifacts. They all show relatively normal retinal nerve fiber layer architecture. And the deviation map or the probability maps are pretty normal. But it's only when we use another type of technique. Here is a new technique that we developed some times ago. We call this ROTA, retinal nerve fiber optical analysis, which allow us to uncover the optical texture and trajectories of individual axonal fiber bundles. It's only when we use this technique we're able to see clear and definite retinal nerve fiber defects evidence in all these 3 eyes. So even we're using the best available technique in the clinic, here we have the OCT retinal nerve fiber analysis, we're still not able to detect glaucomatous damage, and all these defects also show corresponding loss of the visual field. So what are the unmet needs? We need consensus in defining glaucoma in AI studies. We also need consensus in reporting the diagnostic performance of AI for glaucoma detection. Lastly, we need level 1 evidence to inform whether the application of AI can improve glaucoma care. This is actually a little bit more challenging and difficult, especially for glaucoma, because by large, glaucoma progresses very slowly. To illustrate, the application of AI can help perhaps improve patient-reported outcomes to help slow visual field progression. It takes time, and the design of the clinical trials is also very challenging. With that, I'll stop there, and thank you for having me again in this webinar.
Thank you, Chris. All of your work has been central to our clinic on a daily basis. We have your papers printed out and sitting on our desks so we can teach our fellows and residents about OCT. And I'm sure we'll continue to do the same thing for all the work that you're doing with AI. We have some huge barriers to adoption, and it's as basic as just defining glaucoma so that we all agree on what is glaucoma and what isn't. So thank you for that. And to transition to a topic that's related, the application of AI in retina, Dr. Ciku Mathenge will give us a talk that involves a study with real-world application for AI that I think will also answer some of the questions that have been coming through in the Q&A box. So Ciku, I'll hand it over to you. Thank you for joining us.
Thank you very much, Malik, for inviting me to be part of this panel. And thank you also to all my panelists and to CyberSight. So my first engagement with AI was about 10 years ago, when maybe that word was not what was used. I had just completed my PhD, and for my studies, I had set up 100 retina clinics in 100 villages in Kenya. And what I was looking for is presentations of African, out of curiosity, but also out of my own frustration as a clinician in not really knowing what to do with my retina patients. Currently, I do work as a medical retina specialist. And after I submitted and graduated and got my PhD, about 2 years later, I got a call from Tunde Peto, who had been the one who read my images at Moorfields. And she said that there was a group interested in using my images to run this automated retinal image analysis. I had no idea what that was, but I was willing to give up my images for that, because what I told Tunde is I have over 5,000 images. If they can be used for the good of humanity, I'm willing to share them with anybody. So it's quite interesting that Dr. Abramoff, who was one of the leads on that study, is on the panel today. I've never met him, but thank you that you at least included me on the paper. So this paper showed that automated retinal image analysis was as good as Tunde Peto at Moorfields. So that was really interesting for me. My second encounter with AI was through CyberSight. I teach residents and I encourage them to use CyberSight. And the consult where you can upload an image of a patient that's giving you a hard time and as you wait for a mentor to come and give you the interpretation, you can actually upload it to the AI and get an answer. So I heard about it. I didn't really use it because I didn't really understand it. So that was my next encounter with AI. So my most recent encounter is this randomized trial that we completed last year in Rwanda. And what we did is we set up screening at different diabetes clinics, and we divided the patients into a group that would get an instant report using an AI platform, CyberSight AI, and another group that would wait for 3 to 5 days to get a report from the reading center. What we wanted to see was, did that impact their uptake of care? So there's no need in spending resources initiating screening programs if the people who we say you do have DR are not turning up for care, which is a big problem that we have. So was there going to be a change? And really what we found, we now have the evidence to show that giving the patient the instant report, actually majority went to the ophthalmologist the same day because it was more convenient. They didn't have to make another trip to the city to look for the doctor. And there was a 30% increase in uptake of care, but also that they took up care much faster. So that is, in this study, I was really interested in how does AI change the way I practice ophthalmology? We've heard about the technical aspects of AI. I don't really know the details of that. AI in my setup does not have to be complicated. This is the setup in one of our clinics in Rwanda. So to use the AI, we needed to have a color printer, we needed to have a computer with a screen, and we needed a good camera. And I repeat, you need a good camera. I believe that a lot of the frustrations coming out of some of the AI studies are to the choice of camera. A good camera has to be easy for the user to learn how to use. It has to be easy for the patient to understand what they're supposed to do. It has to be easy in terms of the speed of the procedure, and also that you don't dilate patients. And we were lucky to have a really good system. And within 30 seconds, we got a report. And this is our sample of the report that we got from this project. We were very lucky because we had direct communication with the authors of this AI system. And what that allowed us to do was to say what we needed for our purposes. And they were willing to adjust things to suit our purpose. So for example, on this report, the green is the DR screening. So this patient has no DR. For those with DR, we wanted this traffic light coding because it's easier for patients to visualize what we are talking about. So especially for patients with mild DR, I didn't want to just tell them you have no DR. I wanted them to see they're not on 0, they're at 1. And even though we are not referring them, they were not okay. Therefore, they need to keep up screening. But this was very easy for patients to understand. Now, the red part in this report is about VCDR. I was worried about using a system where I tell a patient, you don't have DR, you're okay, and they go home assuming that they have no other problem. Glaucoma is a problem in my area, and when I heard that there's an algorithm that can grade the VCDR, I definitely wanted that flagged for my patients. And the AI authors were willing to adjust and give me algorithms that suited my purpose. So I said, I want one that detects a large cap disc ratio, and I want one that detects that something else is wrong on the retina. So if a patient had no DR but had a huge macular scar, I didn't want that patient to get a green report looking as if they have no problem. So we wanted a report that allows patients to know that whatever problem they have, even outside DR, there was no other diagnosis, but at least it flagged that something was not okay. That communication with the AI authors was one of the most important aspects that I found with this setup. So artificial intelligence can mitigate some of the major barriers that we have in taking care of our diabetes and other retina patients. In my population, there's limited awareness that diabetes, for example, can cause vision loss, or that vision loss is different from cataract and it's irreversible. This is my patient Maria, who came to me for cataract surgery, but had irreversible damage from diabetes by the time we found her. We want to reduce this kind of stories. There's lack of systematic eye screening programs, including reading centers. So ophthalmologists have to be the ones who read the images, and we just don't have enough time or enough of us to be the ones doing that. There are other barriers that are caused by distances to screening centers or the high costs, or just equipment is not available everywhere. And then there's poor coordination within the referral system, such that patients who do have diabetic retinopathy actually don't know where to go for care. I think these three problems in white, AI can help. AI can help by helping the few of us who are there who can look at retinas and tell what's going on the retina, do more with less, because we can delegate more tasks. AI also allows the delivery of quicker results. And as we saw, this does impact how soon and how often patients go for care. Then what we also found is that the diabetologist having this report, it was easy for him to convince the patient to go for care. And the diabetologist is the person that the patient knows. When I go as a screener, I'm a stranger. But if the person who the patient actually came to visit can tell them, look, your report shows you have a problem, then they're more likely to uptake care. And of course, by putting this screening within the diabetes clinic, we are creating integrated patient-centered care, which is where we all want to go. We still have things to sort out in our region. We don't have the relevant technical skills to build AI, and yet we want AI to be built that works for us. I don't know any AI developer in my region. There's also lack of investment in research and development. So that transition from the lab to the market, I don't know how it's going to happen because we don't have investment in that area. And of course, we need to improve some of the basic infrastructure that has been mentioned by others. Internet is still very expensive and unreliable. The legal frameworks that will tell us what AI should do and should not do. And also just to have enough data from our own population to inform these technologies that are being developed. I do believe that even in low and middle income countries, AI can really be part of the solutions that we give our retina patients. And I believe that DR is just the beginning. Thank you very much again for including me on this panel.
Ciku, it's a pleasure. Certainly a pleasure for us that you joined the panel. I know you're very busy, but your experience with AI in the real world is really where a lot of people are trying to go. You're already there. You're implementing it on the ground. And I don't think that should be understated. I think we should celebrate what you're doing. So thank you for sharing all of this information. And I look forward to continuing to work with you and learn from you. So I appreciate it. I'm going to move on to Michael Abramoff, who to me, I know he wouldn't like me defining it this way, but he's one of the rock stars of AI. Certainly one of the original advocates of transitioning from just research, which certainly is valuable, but with the ultimate goal of getting it into the clinic and into patient care. I invited him today to speak about regulatory pathways, but during the Q&A, I'm sure we'll have some other questions talking about his experiences, the good part and the scars from commercializing a device. And we'll get to that in a little bit. But before that, Michael, please speak to us about regulatory pathways.
Awesome, man. Thanks so much for having me. And Dr. Mathenge, so I recognized the name and I thought, where do I know this name? And now I realize we actually did a paper together. So nice to be on this panel together and hope to work together soon. A couple of conflicts of interest. I'm speaking here as an academic, but clearly I have a role in digital diagnostics. So there's a clear conflict of interest, as well as numerous policy of AI, including with FDA. So one of the interesting aspects that indeed we are running into regulation around the world for specifically for autonomous AI. Some of the countries we already implemented in dark, and some of the countries we're right now going to clinical trials, and other regulatory aspects are shown in yellow. And there's one in Bangladesh where actually we are finishing and wrapping up a great trial together with Orbis. So that's in a partnership with Orbis. Very exciting. I wish I could share the very exciting results, but paper should be coming out very soon. Anyway, so some of the speakers already mentioned it, but I did want to establish this difference between more autonomous AI versus more assistive AI, where we as clinicians all use AI probably almost daily. You know, from the Zeiss or Heidelberg, it helps us give us numbers or other analyses of an OCT scan. But that's not the same as autonomous AI, where it essentially does what a retina specialist does, where the retina specialist is not, meaning in a place where there's literally only an outlet with 5G, you know, it's enough to make a high quality diagnosis. That allows you to do at point of care. That also allows you to where the biggest problem, both in low income countries, but elsewhere around the world as well, the access problem is really where the patient is not where they should be, which is with the retina specialist, because there's not enough of them. There's other reasons. And so now you can be where the patient is, rather than the patient coming to you, the AI goes to the patient. And that allows you to solve population health problems that have been intractable, even including telemedicine. So about regulation, I cannot, you know, discuss all the regulations in Japan, Saudi Arabia, in Europe, CE mark, in the US. What I want to do is more a general framework that has been really helpful. And so the first thing, and I'm in Iowa, and you may not know where Iowa is, but it's in the middle of the US, and it's a grain corn producing state, and that's where you have these silos where the corn is stored. And so all around me are these silos, and that is also a term for working in isolation. And so you see a deep learning algorithm there, it sits in a silo, but we shouldn't develop healthcare AI that way. You get to very rosy, unicorn, rainbow type projections. And I think Pearse already set it out. I mean, you know, the real world is a little bit different. Because in addition to just solving the algorithmic problems and the accuracy, there's more general concerns about healthcare AI that people have, and that we had to solve to make and implement it in so many countries around the world. Will it benefit me as a patient? Will it exacerbate rather than improve health disparities? What is going to happen to my data now that an AI is looking at it? Is there racial, ethnic bias? Who's liable for errors? And we pays for all of this. So we have solved this in the US, and we're solving in other countries, and we're solving it with frameworks. So I will talk a lot about that. One mention I want to make is this concept of glamour AI, which is AI that is technologically really cool, but it doesn't solve a patient problem. It doesn't solve a population health problem. It's not benefiting patients, and you know that is not what we're interested in here. And so that these concerns are valid is shown by very recent examples, both in AI, where there was a patient being harmed by AI that has had a lot of effect in the US until today. But the fear of backlash against all AI is real. We have seen it with gene therapy, where in the US especially, gene therapy was making great progress, really on the cusp of being implemented widely. There were some unethical trials, young people died, and it was shut down for almost 2 decades. And only very recently did FDA approve gene therapy, in fact, for a retinal disease. You know, ophthalmology is typically at the forefront of all these new developments. There's other examples I won't go into. But if you want to address this, you need to step out of the silo as an AI developer, as an AI creator, and make sure that all stakeholders in healthcare, that means the creator, but also patients, also in the US, the government, policymakers, regulators like the FDA in the US, physicians and provider organizations, payers, and even ethicists, they all need to be comfortable when you start implementing AI at scale. And we actually made a choice whether we were going to be the Uber of healthcare, breaking the system, which is on the left, or actually working within the system and addressing all these concerns. And that's what we did. And that's why we got, and already was mentioned in the beginning in 2018, the first ever FDA approval for an autonomous AI. But that meant that we had to do an enormous body of work on ethics of AI. It started with ethics, because if you start from the very elementary bioethical principles that we have in medicine, like patient benefit or non-maleficence, autonomy, justice or equity, when you start with these principles and build your regulatory framework, your payment framework around that, you can be sure that there's no gaps, that 10 years, 20 years from now, we will not say, oh, we should have thought about it, because these bioethical principles are more thousands of years old. They're, from every culture around the world, you can see very similar principles. And so that is a way to effectively create a closed framework. And so we published that in 20 after years of work. And the elementary message is really this, that there are varying competing bioethical principles like maleficence, non-maleficence, like justice or equity, like autonomy, as you've shown here, and a doctor, a healthcare system, and an AI sit in the middle of this and are under tension. You cannot be 100% guaranteeing patient autonomy, while at the same time guaranteeing 100% patient benefit. We can talk about why it is. There's always a balance to be found, more of this versus more of that. And different cultures, different healthcare systems, different physicians, and different AI creators will have to make that choice. But there is a choice to be made. And what the frameworks help with is measuring. So if you tell an engineer, be ethical, they will ask you, well, how? And so you need to have a way of measuring how much of an ethical principle you're meeting. And I think that is the principal contribution of this ethical framework, that we say, well, for example, patient benefit, there's different ways of measuring it. Here's the ways you can measure it for an AI. For equity or racial bias, here's how you can measure it for an AI. Autonomy, the same thing, even responsibility. So that was, I think, the contribution there. And that has been really helpful, because we started from this basis. It allows us to do the ethical frameworks, ultimately with the goal of improving health disparities, improving access, lowering cost, and just in general making healthcare more available. So that's the goal. But for that, we worked very closely with FDA and other regulatory agencies on regulatory frameworks. How do you design a clinical trial? How do you deal with bias? How do you develop and conceptualize an AI? How do you include it in the standard of care? And then on the other hand, we're not talking much about it here, but there needs to be, for an AI creator, a business model. For a provider, there needs to be some way of getting reimbursed for it, so that it will be incentivized to use it. So payment frameworks are really important. We also worked very hard on a payment framework, reimbursement framework for AI, and that allows us to have nationwide reimbursement in the US, which was very exciting as of this year. And so just sketching that there's close work with the FDA, the US FDA, which is called the Foundational Principles of AI. They created a so-called collaborative community where we work together with ethicists, with FDA, with tech companies, with clinicians, to create guidelines, or what we call considerations, for how to validate an AI. How do you design a clinical trial? What about transparency and explainability of the AI? How do you deal with federated learning? How do you measure all of this? So that is the work we're doing. The first publication came out now last year, and it's very dense. It's about 30 pages, but it really lays out what you should be thinking about when you want to regulate AI, and especially autonomous AI. And similarly, that ethical framework allowed us to create a reimbursement framework starting from ethical principles. And actually, we published this together with payers, with both physician organizations, especially people specializing in physician reimbursement in the US, but also with government agencies that pay for AI. And so that was really important to base it in ethics and to explain how you can get from an ethical principle all the way to reimbursement that actually works for everyone. I mean, if it doesn't work for the payers, if it's too expensive, they will not pay for it. If it's too low for AI creators, no one will build AIs, the R&D stops. So very important to address all of these. And then finally, a little bit about liability. I didn't hear much about that, but the liability, very important in the US, of course, because of the medical malpractice claims of hundreds of millions of dollars that can be awarded here. But as important in other countries, who is liable for an AI diagnosis, and especially for an autonomous AI? And we have stated very early on that that should be the AI creator that should be held liable, not the provider using it, which typically can be a provider who is not familiar, for example, with a diabetic eye exam, a retinal exam. So all of this and the acceptance of all stakeholders is shown by the fact that the biggest patient organization, American Diabetes Association, including autonomous AI in their standard of care. In fact, they call out IDXDR, this AI. You're not familiar with the US system, but very important that AI is now supporting the closing of care gaps. that indeed CMS, Medicare, pays a national rate for an autonomous AI diagnosis for diabetic retinopathy. They spent years working this out because they want to open this precedent for good AI, for AI done the right way, and not for AI that may actually harm patients. And how do you deal with that from a regulatory perspective? Oh, sorry. And so, yes, we have indeed been able to apply this. We continue to apply it worldwide. Very excited about the trials that are ongoing in these different countries and how we work together with these regulatory agencies. Also very proud, cannot help but mention it, our partnership with Orbis, especially shown by the publication soon to be appear about this great study from Bangladesh. So I haven't been able to say very much about specifically which law or regulation to follow in all these different countries, but hopefully this is helpful to have a more general, oversight of where it's going. Thank you very much.
Great. Thank you, Michael. It was a really ambitious program here to get as many talks as possible. And I had two really intentions behind this. One was I wanted to learn from all of you. I read all of your papers, and this to me was just on a personal level very exciting. But also I wanted to try and create an enduring sort of file that can go on CyberSight. The session in itself will live on CyberSight for a very long time. And I think somebody who's curious about AI can go to that and really learn the basics and start to pick up some of the threads that each of you have left in your talk. Michael just now, each slide could have been a 5-hour session by itself if given the time. And I certainly appreciate that. And I also try in the webinars that I moderate not to go over an hour and a half because a lot of people are busy. But I do want to, the Q&A part I think is super important. I tried to answer a lot of them if you noticed as we were going along, but I did write a few of them down. And I want to ask you some light questions and some heavy questions. And anybody can answer this. I'll try and direct it to one, but then anybody else can speak up. And Pearse, the first one is for you. I'll throw you a heavy one to start with. One of the questions that came up, and certainly when you look at the people that dialed in, we have people from all over the world, different healthcare systems, different resources. How do we make sure that AI does not widen the care gap in some areas? What are some of the pitfalls that we have to watch out for in that AI can maybe help some areas, some populations, but not others, and actually benefit some, and if not hurt others, maybe just not benefit the others who don't have access? What are your thoughts on that? I know you've thought deeply about this, but what can you share?
Well, I think, there's lots of aspects to that question, but one that I would like to highlight is that there is a real risk of something that my friend Alistair Denniston has coined health data poverty. And this is the idea that actually, if we have just developed AI systems on, say, like retinal photographs from like white Irish people like myself in their 40s, then essentially those are very unlikely to work in different populations, different ethnic groups, etc. And so I think there's a real risk that our systems won't generalize. Because as Jayashree said in her talk, the fact of the sort of the Achilles heel of a lot of the modern AI approaches is that generally they don't perform well on data that's different from the data that they've been trained on. And then sort of related to that, another point is that we see that ophthalmology in some senses has been at the forefront of this through Michael and other work. But I think part of the reason for that is that there's been large ophthalmic imaging data sets, some of which have been made publicly available, like Mesidor and IPAX and some of those data sets, that has really stimulated a lot of this. So the machine learning experts, if they're interested in doing some medical imaging applications, they can get access to public ophthalmic data sets and they can start to test their algorithms and develop their algorithms. But you see in some other medical specialties, like obstetrics and gynecology, at least as far as I know, there isn't really a large number of these public imaging data sets. And as a result, it's not so common that you see cutting edge clinical AI papers in those specialties.
Right. Maybe Michael, I'll throw the question to you because you have the real world application part of this with digital diagnostics. So how did you ensure that your data would be applicable to a wide range of population?
Well, there's a more general question, which is even from the concept stage, if there's, for example, I mentioned these tension between these different ethical principles, and it comes back to that. If you want higher performance, it may require more expensive scanner or imaging camera, right? It's easier to get high quality images from just high quality operators who are very expensive. But by even that choice, instead of maybe a lower cost imager where, you know, the AI needs to, with higher performance, needs to compensate for lower quality inputs, more noisy inputs, even those choices affect how ultimately whether you're going to affect health disparities or not. So rather than a single answer, it starts from the concept, how you train it, which is another thing that Pearse mentioned, right? Include very diverse data sets, make sure that you also validate it on very diverse data. And that's why I was so happy to collaborate with Dr. Mathenge years ago, where we had this algorithm indeed developed mostly on European data, both North African and European, and they were able to validate it in Kenya, which was, you know, very exciting because that was a big concern at the time. We have chosen to look at biomarkers, right? So typically we do not train from blind images, but rather we say, well, a hemorrhage, an exudate is racially invariant. If you have it, doesn't matter what background color of the retina or what pigmentation. And so that is a longer discussion, I think, but there's ways to address and mitigate this. But my point is more, there's a lot of choices, even at the start, that you make that will affect whether or not you're able to solve health disparities.
That's great. Yeah, and this kind of throws a question to Chris from some of the content that Michael just talked about. So one of the issues here is quality of data. And the quality of data can be thought of on two different levels. One is when you're training a system, when you're trying to see if you can actually take it into the real world. But once you get it into the real world, and Chris, you've talked a lot about OCTs that are giving you valid information versus maybe overcalling or undercalling. How do you think we can adjudicate the information that we're obtaining from AI in the real world? So I'm in clinic, I'm seeing patients, I have an AI system that is helping me with OCT. How should I think about this as a clinician when I'm getting that data? Should I believe everything? And how would I adjudicate? How would I actually figure out what's right and wrong?
It's not easy even for specialists. I remember when the spectral domain OCT was introduced back in 2005, 2006. Back then, they have the series had the display. They call this retinal nerve fiber thickness deviation map, which show where the retinal nerve fiber thickness is below the normal reference range. Now, that was not an AI algorithm, but in our locality where we have loads of individuals with high myopia, we see all these defects all the time. They are, you know, all around the superior pole, inferior pole. In the beginning, I was, wow, this is how high myopic eyes, they are susceptible to development of glaucoma, which we didn't detect. We were not able to detect. I mean, before we had OCT, now we had the OCT, we see all these defects. Right. I think the same thing happens here. You know, we really, especially for new technologies, we have to be very careful. We always need to integrate, especially for glaucoma, we need to integrate prospective data. We need to follow the changes of this and the retinal nerve fiber over time to ensure that this is a progressive type of neuropathy, this kind of gold standard we're using. But unfortunately, a lot of time we will not have that, and I think that's why it's not easy. That's why we don't yet have a consensus how to define glaucoma. But again, I think the integration of using both fundus photograph pictures, using OCT, using other clinical information together is critical to judge whether the test results we're looking at is true or not.
Yeah, that last part I think is key key for me in my practice, right? So when I'm looking at a visual field OCT or photo, that's a piece. Each one is a piece to the puzzle. We can think of AI much the same way, that it's assisting what we're doing. It's not dictating what we're doing, and it's just going to be a piece to the puzzle. So I appreciate that answer. Jayashree, I'm going to shift gears a little bit and force you to talk about the differences between what your experience has been in radiology versus what you're seeing in ophthalmology. What can we learn in ophthalmology from your experience in radiology, and what radiology has already done? Arguably, radiology is the most advanced as far as applying it to their day-to-day practice compared to what we're doing. And I know Michael might disagree with that because it depends on how you define AI. But what would you say about differences between radiology and ophthalmology and what we can learn from radiology?
So I think the problems are similar in many, many ways. I think for both fields, infrastructure is a key component of doing it for real. And the notion of DICOM and sort of interoperability between imaging formats and not having proprietary formats, things like that really can limit how easy it is to apply AI. And I think really pushing towards standards is something that radiology has been doing for a number of years, and ophthalmology is gradually getting there. But I don't know if it's my perspective, but I feel like the interoperability and the adoption of DICOM and PACS and things like that are not as ubiquitous as it is in radiology. Again, radiology has, I wouldn't necessarily say that one is necessarily ahead of the others, because radiology has also very complex data sets. Like MRI can be very, very complex. And again, the same practical aspects of figuring out which image to apply the AI to is not trivial. So in many cases, it really does come down to very mundane, sort of boring things like the plumbing between systems and the things that nobody wants to talk about but take the most time, which is just the practical aspects. Is this the correct image? Are you feeding it a cat or an eye, kind of thing? So input validation, quality checks, things like that, I think are common to both. They're not necessarily solved in radiology either. So infrastructure, I think, is just, again, I cannot emphasize enough how important things like that are. So.
Yeah.
But I think we saw this with the COVID in radiology. There was like an explosion of really terrible publications that used AI. And I think we have to be sort of cautious about that here as well. These what they call Frankenstein data sets, where all the COVID positive cases were from adults and all the negative cases were from pediatrics. And the model did a great job of separating pediatrics from adults and things like that. So, I mean, that has been brought up for others as well, this notion of bias in data sets. So I think there are lessons to be learned as to what not to do, the amount of money and effort and resources that have gone into this awful amount of publications, I think is a cautionary tale for all of us. And we need to, again, learn from those experiences.
Yeah, no, that's great. I think we can maybe learn a lot about what not to do because some of the mistakes were blazed by others before us, and people like you and others on this panel, I think, will keep us honest. Some of the questions that came in had to do with how do we obtain data, how do we obtain the right type of data, and question for Gabriella. Can you talk a little bit about the approach that Orvis takes to obtaining data? What's your philosophy when it comes to gathering data from around the world, or anything you wanted to touch on from the experience that you have within Orvis?
I do have a lot of experience with this, as it was my main role in the beginning when I first started working here, was collecting data. I think Orvis's main goal when it comes to data is diversity. And I know it's been mentioned a lot, but I don't think it can be mentioned enough. You need data for global representation, as this is a global problem in terms of eye care. And we take a very, I'd say, personal approach in this. So we get a lot of data from, open source things such as Kaggle, DR dataset. We partner with a lot of healthcare systems and hospitals and clinics. And I think that, like I said, diversity is the biggest issue in terms of training AI and using AI. And you can't expect to use an AI system in an area that it hasn't been trained in.
That's great.
Diversity is key.
Absolutely. And I think that's a theme throughout some of the questions that we got in some of the lectures that we heard. So fully agree with that. So Ciku, I'm going to ask you a question and give me the honest answer. So let's say you were talking to a philanthropist and they were writing a check for you and they said as much as you want, right? So what would you do next to follow on the work that you've done with raters? Forget about the financial limitations of what you might want to do. What would you do that might impact your day-to-day clinical life as a next step to the rater study, which I think was fantastic. It gave us a lot of information. So what's next?
So we do intend to take that next step, and we've started it in a small way. And some of the things that are really needed at this time have nothing to do with imaging eyes and uploading to AI. It's the health system changes. For example, how do we charge for this new activity? Because I'm not gonna keep getting free AI from Orbis forever. So I need a tariff in the health system, and how is that tariff determined? We have an AI kind of department in Rwanda, but it's just in its formation, and it's exactly to guide on such things like, you know, where do we develop storage in country? Does storage go outside? What do we do with people who come and deposit cameras in clinics and say, just keep taking images and sending to us, and for every image, we'll give you something. So I think it's a lot of those other things in the health system and in the regulatory system. Those are the things that I'm finding are a challenge now, rather than affording a camera or a computer for a clinic.
Yeah, a great insight. And it kind of touches on something that Michael said earlier about the reimbursement part of what we're dealing with in the US. So if you don't have a business model, you're not going to get the innovators working on it because it's not sustainable. It has very little to do with the intentions of the person, but more so with the reality of being able to carry projects forward. You have to get paid for it so that you can keep innovating. Would you agree, Michael?
Yeah, great point. And what is exciting about the study specifically with Orbis in Bangladesh is that we're looking at, you know, what can the business model look like where it both works for a low income country, but on the other hand, it's still interesting enough for an AI creator where, you know, because if it doesn't work in the US with a business model, you know, it cannot work in Bangladesh either. So I think we're solving that. And so that's very exciting because that allows you to scale to many other low income countries. But if we don't solve that, it will be philanthropically, and it's hard to sustain long term, right? Like you said. So completely agree. Yeah.
All right. So the last question here, just for time's sake, is going to be to Pearse, because it's become sort of a pastime of mine to put Pearse on the spot with every session that I do with him. So I want you to close off this session. Remember, this is being recorded and will be online forever. And to tell us where you think AI in ophthalmology will be in 5, 10, or 20 years. You can pick whichever one you want. I want you to make that grand prediction, and we're all going to hold you to it. So go for it.
Oh my goodness. So, well, first of all, I would say I don't see AI replacing doctors anytime soon. So certainly within my lifetime, within my career, I don't see it. Like, so what I imagine is, imagine the clinic in 2030, and the reality is probably we're going to be just as busy with our patients. We're going to be still like skipping lunch and clinics running late, but we're just going to have new problems to deal with. And I imagine us in the clinic in 2030, 2040, and you know, we have a patient in front of us. We have like 10 different types of advanced imaging. We have their genomic information, their proteomic information, their metabolomic information. We have information from their Fitbit watch about their, or a ring on their finger about their sleep patterns. We have information about the pollution levels in their neighborhood for the last 3 months. And then we have a range of narrow AI tools that somehow draw some learning from each of those modalities. And then somehow our role as clinicians will be to integrate that information to plot the best course for that patient and to convey that with the sort of human empathy and care and all of the things that makes us good, I would like to think, good doctors.
I love that answer. I love that answer because it also focuses some of our training habits that we have to do for our residents and our fellows, that the human factors of what we're talking about and how we deal with the information and how we convey the information is becoming more and more important with the addition of technology into our clinics. So it's kind of the opposite of what people feared. We're actually going back and saying, okay, how do I convey this information to the patient? How do I speak to the patient appropriately? So I'm excited for the future. I'm excited to go back and watch this entire session when it's up on CyberSite. So just to remind everybody, Lawrence will work very hard to get this up on CyberSite, probably sometime next week. If you can go take a look, sign up, make sure that if you're in a group there that hasn't signed up individually, sign up for CyberSite so you can get all of the updates. I want to thank each and every one of the panel members. I've learned significantly from each of you throughout the years, as well as today. And I would hope that we can come back and do the same thing in about 10 years and see if Pearse was right. So don't forget the answers that he gave. So I want all of you to have a great day, great evening. And to all the attendees, please reach out with any questions through the Orbis and CyberSite systems. Thank you, everybody. Have a great rest of your day.